Today, our webinar, we have two presentations. The first presentation is about IoT sensor network for water quality monitoring. And the second presentation will be about the actual system, we say Aqua Watch, developed by CSIRO, and Dr. Zui will present about that very interesting system, and with the combination of sensor and AI. So the first presentation, my name is Dung Dao. I'm professor in mechanical engineering at Griffith University. And okay, so let's start. So this is some point outline of the presentation. Give some introduction about the importance of the water quality monitoring, and then some enable technology for the IoT sensor network for water quality monitoring, including the sensor technology, IoT communication infrastructure, and IT, and mainly about the data analysis and AI. And finally, we introduce some IoT sensor network that developed at Griffith University. So as you know, that water is very important for our life, especially the clean water is important for sustaining life and for the productive agriculture, aquaculture, and healthy ecosystems. So in the past, people use the manual technique to get a sample and to check the quality of the water. So that method is infrequent data, is a slow process, and is inefficiency. Okay, so we are now living in the IoT era with the Internet of Things, with AI and sensor. So that is the solution for modern and smart monitoring technique to give you the real-time response, early warning of pollution, and better resource management. So the IoT, I think everyone have heard about this in the last 5 years, especially. It's Internet of Things, refer to the network of the physical device, for example, sensors and the other device, machine, robot, that are connected together through the internet. So that is the concept. So everything is connected through the internet. And we have seen this application in smart cities, agriculture, environment, transportation, in industry, automation, and so on. So the key technologies for the IoT smart water quality monitoring is the first is about the sensor technology. We need the sensor to convert the environment information into the electricity, so that we can transmit that signal. We can measure, we can transmit a signal through the internet. And the second important technology is IoT communication. So this is about the wireless communication network, and also about internet. And the last one is about the IT infrastructure. It includes the data center and data analysis using the AI, and then give the user the prediction, the warning, and some kind of recommendation. So this is the key technologies, okay? And to support the smart water quality monitoring. So the first, so if you look at the architecture of the IoT AI sensor network, we can see this component. So the first component will be the sensor. We say the sensor node. There are thousands of sensors, millions of sensors installed in the field, for example, in the lake, in the river, to monitor the parameter, the water parameter. For example, we have the physical parameter like temperature, turbidity, conductivity, the salinity, and so on. We have the chemical parameter, pH, dissolved oxygen, and then we have the biological parameter, and so on. So that is a sensor, million of sensors. So the sensor is connected to the gateway where the data will be sent to the internet and stored in the server and in the data center. And next, the application server, the user can access to that, can access to data and can display or can see, visualize the data. And that is like 5 or 10 years ago technology. And recently, with the emerging and the success of the AI, so the AI is important to access the data and can produce the very smart and early warning and prediction to that. For example, if the water is polluted with the bacteria or with the salty or algae, a lot of pollution happen in the water that can be detected, can be analyzed, and can be given. The user can be given the advice what to do next. So so the three component: sensor, IoT communication, and AI. Okay. So the first we go to the sensor. For the water quality monitoring, what kind of sensor are needed? Okay. So we have the how can we put this one? Okay. So we have the physical sensors that measure the physical parameter. For example, the temperature sensor is important for the aquaculture fishery. It's very important. So common type of the temperature sensor is thermistors or resistance detection, temperature detections. This is very basic, but based on thermistor, based on semiconductor, and second type of physical sensor for water quality monitoring is turbidity. Okay, to measure how clear, how clean is the water. High turbidity can affect the life of fish or of the prawn. So aquaculture, and I think Dr. Zui here is one of the experts in this kind of sensor and monitoring in the shrimp lake. We have other sensor, conductivity sensor for the salinity to measure the salty, how salty is the water, and total dissolved solid in the water, and also the water levels to measure how high is the water availability of the water in the lake or in the pond and in the rice field and so on. So this is a physical sensor. Also, we have the chemical sensor. Right? So basically chemical sensor to measure the chemical reaction and convert that signal, ion and electron and holes in the liquid into the electrical signal, so that we can measure. And some parameter here like a pH sensor to measure the how is acid or is alkaline environment. So this is very crucial for aquatic species and for aquaculture, agriculture, drinking water, and so on. So the technology for pH sensor is this is some example. Is the ion selective field effect transistor. Is the most popular technology to measure pH sensor. Also, we have the dissolved oxygen sensor. So oxygen is very important for aquatic species, fish and prawn. So it's important to measure if we have enough oxygen in the water. And we have a technology currently using the electrochemical. Is also convert. It measures the ion and electron in the liquid and convert into the electrical signal for the measurement. And also the other sensor here, heavy metal sensors. This is quite a toxic metal like lead, cadmium, and mercury. So this kind of the metal in the water will very toxic for aquatic for human being as well. So measurement of this is important, and also using electrochemical, we can detect this kind of the heavy metal. Chlorine sensors. When we drink water, we can see the chlorine is for the disinfect. But if it's too much, it also affects the health of our human being and also of the aquatic species. Maybe also other chemical sensors, but here is some typical chemical sensors to measure the chemical parameters of the water. Also, the other parameter is biological sensors. Sensor, for example, for the, detect the algae sensors. The algae is sometimes very harmful for the species in water, and I think Dr. Edo here is expert in detection of algae. So maybe so the typical technology is fluorescent-based sensor. So it means that we use optical, we use the light to shine on the algae, the water, and it will absorb and excited and emit the other light with different wavelength. So we can use an optical sensor to detect that emitted light, and we can see the level of the algae. So the next one is a bacteria sensor and so on. So I'm not the expert in the water, but I hope we have here, you know, if you know any other kind of the parameter that we need to measure, our group is working on the sensor. We can develop the sensor for measurement of those parameters. So in terms of sensor, we say IoT sensor. I mentioned before, for IoT application, we need millions of sensors. The sensor is connected to each other through the internet and send the signal over the internet to the server and to the data center. So we need many sensors. So because we need many sensors, we need something cheap, something small, something low cost. Right. And so that is we talk about the MEMS, the micro electromechanical system sensor technology, because if you can see here, we can fabricate thousands of sensors on one silicon or semiconductor wafer. so that we can make the low cost and very small size and consume less energy. So today we don't talk much about the sensor because we have a limited time. But this is the name is technology is MEMS sensor technology. Yeah, you can see here, this is one silicon wafer. We can develop thousands of the sensor chip like this, and you can make the cost lower and more high precision. Okay. So after sensor, we go to the IoT communication, as I mentioned, or internet. So the important communication technique here you can see we have different type of communication technology, and to evaluate the communication, we have the first about the data rate, how big volume of data we can send and how fast send. So this is a data rate, and also how far, right? How far we can send the data. So this is a range, right? Like a few tens or few 10 kilometers. It's a range, and also about our consumption, low power consumption or high power consumption. So that those are three important parameters for wireless communication. We are very familiar with Wi-Fi, right? Wi-Fi here, for example, is a low range. It can be like a 20 meter, but very fast, very rapid, fast. A lot of data can be sent, but also consume also high. The other type of communication using is cellular, 4G, 5G that we are using with mobile phone. This also very high power, fast data rate, and about 1 kilometer or something like that for IoT, because IoT, when we collect data from sensor, is very small amount of the data. We don't need a high data rate. So like if you measure temperature, very small amount of data needed to send, and we don't need to send the data continuously. We just send data like every 1 hour or something like that. So we need something more suitable for IoT. And here you can see we have the long range. In that case, we can send the signal in 1 or 2 or even 5, 10 kilometers range, and also very low power consumption. So this kind of technology is suitable for IoT sensor network. Maybe you have seen LoRa and NB-IoTs. Now I talk more about this LoRa and NB-IoTs. Okay, so we have seen this one for technology selection for IoT communication. Depending on power consumption, we need a lower power consumption, but we want something larger coverage, and so data transmission volume is not so important. We need security sometime and investment cost, okay, to select this one. So for low power wide area network technologies, we mentioned before, there are also two types, licensed and unlicensed. License means we have to pay money. We have to get the license. We have to pay money to get to access the network. These include NB-IoT, narrowband IoT. We have to pay, for example, using the SIM card to access to the 4G and 5G. But it's different from the normal 4G and 5G. Here for NB-IoT, we can control, optimize the time and the data sent So that is in NB-IoT. And for unlicensed, typically we use LoRaWAN and Sigfox. That are two technologies. So for unlicensed, we don't need to get the permission to use, and we don't have to pay money. It's free to use, and also it's suitable for remote area where 4G or 5G are not available. Okay, so that is we say LoRaWAN. LoRa mean long range, and Sigfox, those two technology are suitable for those in remote area. Yeah, so I think typically we can see the comparison between licensed and unlicensed and some pros and cons in here. This is some example of the system when we want to use IoT sensor network to monitor the water quality for agriculture and for aquaculture. Okay, so for example, if you can see here, you can have a station on a lake. It can have a sensor to measure the water parameter that we mentioned before, and have the solar panel to get the energy and transmit the signal through the LoRaWAN sensor network. Also, we have the sensor to measure the water in the rice field, for example, or in the fishery lake, and the send signal to a gate, or we say the LoRa gateway. One LoRa gateway can collect wirelessly data from hundreds of small sensor nodes and send that signal to the LoRaWAN server, and we can send to the data center for the further data analysis like AI. This is example. We have a very beautiful rice field where we can put a sensor to measure the water level, the salinity, like salty, pH, oxygen temperature in here, and then we can always monitor real times and can have some response to the case if something happened. This is in Japan. They use the sensor. You can see the sensor here is immersed in the water in the rice field, and this is the wireless communication to send a signal. Also, the IoT sensor network for flood monitoring. So this is one of the projects that we get supported from Australian government 2-3 years ago to develop the sensor network to monitor the water level. This is for flood monitoring, and similar, we have a sensor plug in the area that frequently affected by the flooding, and the sensor is underwater here, and the signal is transmitted through here. About 50 flood monitoring stations, the sensor node were developed and installed in Ho Chi Minh City, and is connected through the LoRaWAN and display on the mobile phone app. Is successful in 2023. Also, that IoT can be used for the other infrastructure monitoring, landslide, or the in the highway, the displacement of the soil, and so on. And at Griffith, we developed those kind of sensor, like a tilt sensor, pore pressure sensor, and strain sensor, that also connected to the internet. For example, if you go to one of our site here on the campus, you will see something, the yellow pipe, something like this. Is sensor is go very deep inside the soil, and it measure the movement of the soil and the water pressure and the temperature. And if you click to here, for example, we have one node here, and we have other node in other places. But one node here, if we click, we can see. Let me see. Okay, so we can see the real-time data is collected on the site. Hopefully it works. So now it's retrieving the data from the sensors. We have the tilt sensor to measure the tilt. That means how much the soil is displaced, it's moved because of the pressure or something infrastructure. And this is around axis. So you can see now it completely no displacement, but the sensor is reading. We can see over time. You can see over a week or month, the data is recorded. And also we can measure the pressure. For example, if we have some contraction above that ground, the pressure will be increased, and we can monitor the increase of the pressure. And if we have the water like a rain, then also the pressure increase. So those parameters are important for civil engineering and so on. Temperature, also we can measure temperature under the ground. You can see here, for example, we have 5 sensors to measure temperature in different depth. This is close to the surface, the temperature around 15 degrees Celsius today. And this is 1 meter from the surface, temperature 17 degrees. And then this is lower, right? 1 meter, 2 meter from surface, 5 meter, and the temperature is almost constant, right? After like about 5 meter. Here temperature on the surface, you can see it's lower, but it will be increasing. If about noon, temperature will be increasing, but this is midnight, temperature is low. Some example, that is example of a multi sensor to measure multi parameters and transmit to over internet through IoT sensor network. And I think that is the last slide. Let me see. Yeah, that's the last slide of the presentation, and thank you very much for your attention. So maybe, thank you, and maybe to save time, we will start the second presentation, and then we have some time for question Q&A at the end. So are you ready?
Yes.
So the second presentation is given by Dr. Zui.
It's really good to see how we design the sensor. I'm one of the sensor user, but I want to start my presentation with it one that I actually steal from Professor Kate O'Brien yesterday in the World Lake Conference. The quote saying that no one trusts the model except the person who built it, and everyone trusts the data except the person who collected it. So I guess did it because today I want to talk about how I use my model to try to describe the physical part, and then I also try to combine that with AI the thing that not many one actually trust. So that's why I think this slide something that I want to make a transition between the presentation from Professor Zoom when we collect the sensor data from the sensor. And I am at the modeler who build the model, try to retrieve the data. So today, I will talk about how we use model for water quality monitoring and forecasting. I want to acknowledge all the author and my colleague there, and all the funder and CSIRO. And before beginning, please be aware that I'm a physicist. It means that my background is in computational fluid dynamics. I'm not an ecologist or a biologist. However, today I still try to talk about environment monitoring. It means that there's a lot about ecology here. So I would try to answer all the questions on that, but I guess here today actually we have Professor Ha here is one of the person who work on health as well. So maybe you could also help me with that. So the talk is actually first I will give a brief introduction about the CSIRO AquaWatch technologies. It is the ground to space water quality monitoring and forecasting system, and then I will go on to describe the model that we built in AquaWatch and give a example on how we do that with cyanobacteria forecasting. Why cyanobacteria? It's because, like Professor Jung said before, and also Edo is here, algae bloom is not just threatened, but it is the most common biological or ecological issue that when we come with dealing with water quality. And for me, it's interesting because it's not just physics. You deal with biology, you deal with a lot of things to model it. So it's also an interesting to model. And I will talk about the theory, the result, and limitation, and how we overcome that limitation by using AI. But to set the theme for the talk, so water quality is a global challenge. And you have a lot of extreme events and due to climate change, due to human activity, but you can see that many coming with flooding, fish kill event, pollution, or harmful algae bloom. As a matter of fact, that right now in Nghệ An province, it's also experiencing a heavy flooding in Vietnam. So when we talk about it, it also very relevant to people there because a lot of people there, they need clean water. And for clean water, it necessitates a really good system for monitor and forecasting. And that come in with the AquaWatch. So AquaWatch is the system that we actually use. It's a comprehensive system that we build to use ground to space sensor, and then connect with Earth observation satellite and modeling. So we actually, you can see the flow chain here when we coming from graph sampling to in situ sensor that Professor Jung just talked earlier today, and combine that with satellite imagery. And then with the power of computer and the modeling, we could give out the early warning or forecast for the end user. AquaWatch is actually a very ambitious program in CSIRO. And it is a research program, but it ran for about 10 years. And it launched in 2023. So it's just only very young age, it's just 2 years. But we hopefully that in 2026 will be some of the operation will deliver to the end user. All right. And to actually monitor water quality, you need to overcome the challenge of complicated temporal and spatial resolution. So you know that in process in aquatic system, it run across many time scale. So you have some seasonal time scale or hydrology scale that could run in the weekly resolution, but some certain event like a overturn in the lake, a mixing event in the lake, or overturn of stratification, it just happen under hour. The same for spatial resolution. You could want to model a reservoir with about 10 or even in the order of 10 kilometers. However, when it comes to small lake like an urban lake or a water treatment lagoon, or even come to a river rig, some river rig is only about 10 meters wide. So to come through a range of a broad temporal and spatial resolution like it, we actually need a new way or new technology to deal with it. And that come the system of another technology is also sensoring technology that we developed in CSIRO. So this one we call that the HIRA spectra. So the HIRA spectra, it actually it comes from a hyperspectral camera when we use the reflectant data to try to estimate the quality or the parameter in the water. For example, some of the reflectant index that we developed for turbidity, for chlorophyll. Chlorophyll is the reflectant you get from algae, and some of the solid or sediment. We install that on many lakes. If you're not familiar with Australian lake, so you have Grahamstown Dam, it's around Newcastle, in north of Sydney. This one is the drinking reservoir. You have Lake Hume. It is an irrigation lake in the south of New South Wales, in the border of Victoria and New South Wales. This is irrigation lake. Lake Tuggeranong is a small urban lake in Canberra. And you also have a treatment plant. It is the Melbourne water treatment plant is actually the largest treatment plant in the Southern Hemisphere. So a lot of characteristic and a lot of lake that we install the sensor, not only HIRA spectra, it need to also combine other stations. So we also combine with standard monitoring technology. By doing, for example, one example here, we implement that in Lake Hume. You see a HIRA spectra camera here. It collects the data every 15 minutes. You also see a meteorological station here where you could get the air temperature, the wind speed, the humidity, and many of the weather data. We have a thermometer chain for water temperature profile, and also water sampling for cell count and many more. And this one, you can see that this one, it complement with the satellite, will allow for the cover of satellite system, and it also to drive the hydrodynamic forecast model. And all of this is actually connected a 4G network. So we actually have a constant data stream and update in real time. Okay, so that is the AquaWatch monitoring system. And now come to the model. So I guess that because a lot of people, well, I don't know who is in the audience, but I assume that not many one know about it. So I will try to explain it one in more of the common language that you could understand. So this is a lake. And in a lake, you can see that this is the sun. The sun will have the radiation, long wave and short wave radiation, penetrate into water. And you also have the wind flowing on the surface. And you know that both the heat and the wind will rise how the dynamic in the lake. In the same thing when you cook, you boil the water on your stove at home, it will give also lighter water, hot water or warm water is lighter, and cold water is denser and heavier. It will be on the bottom. And because of the wind mix, that one, it will give us some certain convection event in the lake in here. And it also gives you some of the temperature gradient. And what the modeler do, the modeler will try to describe that using mathematics or object equation here. You don't need to understand what is the equation about. It the equation will tell you how of all the law in physics, like the balance of momentum, balance of mass and energies, and it's also described using the turbulent model. It means describe how the dynamic of water going in there. So it's the basic, if it go all the way to the basic, it is the Newton second law equation. Yep. And in my model, when I run the simulation, the output from me it's a matrix of temperature and mixing or diffusivity in the lake. And I use that to actually derive the next part of the model. It's called the biological competition model. So this one I will try to describe how the population of the algae growing in the lake. And algae, it actually depends on a lot of things. You know that it's a living thing. It will depend on the temperature, it depends on light intensity. It also depends on the nutrient, and all of those things combined with the dynamic of mixing that I got from the hydrodynamic model earlier, put them into here. You could actually model the growth of algae or phytoplankton. Of course, you can see that all of the equation here is not enough. So you can see the algae could actually fight each other, eating each other. So there are a coupling between them. And there are also many species of algae, not just one. So just one is also the limitation. And also you can see algae also depend on a lot of chemical processes. And just one and only describes some of the physics process. So of course there are limitations. However, if you want to model biological process, and then you want to describe everything, the model could have like 1,000 pages of manual. I don't believe that we could actually describe everything, but for my model, it depends on light, depend on temperature growth, and mixing. So that's the three things. Okay, and to give it more specific, this is the schematic process chain of the model. So the model driven by meteorology. So you will know how the air temperature, the humidity, the wind speed, the light radiation. You get that from meteorological data. You put that as an input into the hydrodynamic model, combined with the initial condition on temperature, flow field. And then when you run that, like say that it will split out to you the temperature and diffusivity. You put that into the grow model and driven with the initial, so the initial cell count. From there, you could actually get the concentration or the number of cell count in the water. And how could I run it at a forecasting system? So you remember we have the high draft spectra that I talked earlier. So this high spectra will give you the data, reflectant data of chlorophyll alpha every 15 minutes. It means that every 15 minutes, I could derive some certain concentration of cell count in the water. And if I give that data into the model, and then driven by the forecast weather or meteorological data, then it will give me a process by forecasting system to forecast cyanobacteria. All right, so some of the results here. So this one is just try to model the temperature stratification in Lake Hume. And you can see the thermometer chain. It is the one that we measure. This is the simulation. You can see the similarity between, so it in terms of temperature, it actually give a really good results. However, you could also see that the model is not equipped enough to deal with some increase of the inflow of the cold water. One of the reason is because the model that we use here is 1D, it's not 3D. Why we use 1D is because we want it operational. It's very expensive and costly to build an operational 3D model for this type thing. We also try to model how the species grow, so changing the optimum growth of cyanobacteria. So Chrysosporum and microcystis here, they have different growth rate. And when modeling that, you will see that the concentration also changing. And one of the things that people also care about is the cell count. So this is the cell count that from the model, it the black line, continuous black line here is from the model. All the scatter dot here, it derived from the higher spectra. And all of the colorful dot here is from sampling. And you can see that here the cell count in the number of cell count per milliliter and all that. There is a disparity between the model and the sampling. However, the model actually is still really good in capturing the cell count bloom. What is cell count blooming is when you have so many growth of algae in the water, and algae like microcystis, they produce toxin. It's not good for human health, animal health, or aquatic health. And it also the reason of so many fish kill or fish death event, because when algae growing too much, and then when it die out, it consume all the oxygen in the water, so it lead to fish kill, and you want to capture that. And normally people have a threshold, and one of that is the World Health Organization put a threshold of 50,000 cell count per milliliter. It adds a red alert, and for example, one is in Lake Hume in in February 2020 here, when the Water New South Wales actually put out the amber alert for algae bloom in Lake Hume, and this is also captured by the model. The next one is also one of the meaningful is the one for changing operational in a dam. So you know that in a dam you have some of the outlet. So some dam you have the outlet for drinking, the outlet for irrigation, and the outlet for hydropower. Those outlet will have a different water depth, and cyanobacteria normally it's buoyant, so it's in the surface. But if the water level is decreasing, it could, all of the cyanobacteria, it actually could be sitting down into the outlet. So you want to know that it actually sit the cyanobacteria in the outlet for it means that the dam operator could know whether they could actually open the dam to release the water downstream. And this is meaningful for project like Edo project in Thailand, when you deal with many eutrophication of reservoir. But I also want to notice that in Vietnam, eutrophication is not a big problem, but the big problem is the accumulation of many sediment. And they also want to know that whether they open the dam, how the sediment will be transferring down to the downstream. And at one of the parameter that we get out earlier is actually the turbidity and sediment transport. And we could do the same rule for the modeling and the same rule for installing the higher spectra. And of course, there is short-term forecasting. So we run a 7-day forecast weather, and we use the actual meteorology. And you see the pattern index is very well described. So all the colorful line here is that when we run the forecast every day, and except every day, you can see that it also very closely with the baseline level, and the higher spectra is the scatter dot that you see here. However, like I say that the model is not without limitation, and clearly you can see some of the limitation is you cannot model many species. So the species actually change over time. It is whether seasonal or annual. And also you can see that the biomass is also different, because other people who work in health, you care about the toxin. You not care much about the cell count. You care the how much toxin or the concentration of toxin in the water. And the toxin also depend a lot on the species and the biovolume. And that is also one of the problems that we run into when the more we try to modeling the species grow and cell count grow by using particle model. And of course, the next thing is because we use the hyperspectral data. So it is camera above water. It takes the photo, the picture of the water on the surface through hyperspectral wavelength, of course. But you know that it only somehow describes a part of the surface appearances of things on the surface of the water. And then from that, we give a proxy on estimate of everything in the water column. And to actually make that estimation, you need to know the dynamic of mixing. You need to know how it transport from the surface down into the base of the lake. And all of that, it actually is unknown. So many of the lake is not have very well equipped with monitoring system to know the dynamic of the water in there. So surely that you can see many uncertainty, right, ranging from 1D mixing model to the mixing dynamic, to species composition, dominant species and toxin. And then you also forecast by on cyanobacteria index from hyperspectral data. So the question here is how we use AI or machine learning to have to improve it. The first thing we want is to clean out the data. So data normally it have gap. So the gap come from maybe the temporal resolution of the sensor, like a satellite data, a Sentinel-2 satellite data only give you the data every 5 days. And during that 5 days, it also happen that you have many cloudy, you have a rainy or storm, then you don't have the data. So how could you fill that gap? And here we build a data gap filling using the time series foundation model. And we try to test it with the lower Murray data in here. And we run the model. You can see the model diagram here. And we try to test the model with 3 parameters: turbidity, TSS, and chlorophyll alpha. You can see that here it's all the gap and how it fills the gap by using time series foundation model in here. This is actually good because foundation model is something that a lot of people talking about now today. And one of the GPT time series, it could actually really good on processing time series data. And we combine that with environmental data like this one. It means that it could help us on provide a continuous time series data to run the model. So that is one of the first limitations that we could solve by using AI. The second one is, like I say, that we don't know the mixing dynamic. So could we use data to actually predict it? So here we also build a prediction of non-mixing in river flow using the data or AI data-driven approach. So this is the case study also in the Menindee in a region in Australia. Menindee is a very hot region recently because of the 2 FitQ event in 2019 and 20. And recently in 2023 and 24, it like 10,000, even 100,000 feet were killed in Menindee. And here we propose a hybrid mixing approach between AI and physics. So basically, we combine all the physical part that we could get and then put that into the neural network of AI when we're training it. So you could put the physics informed neural network, and then we also put a lot of derivation of quantities, and then put that in the classification algorithm when we train the model. So it means we combine between the hydrodynamic or physical based model and the AI, and we try to test it out with one work best, because you know whether maybe only AI work better or maybe only hydrodynamic model work better. We also run an XAI. So XAI is like try to find the local and global parameter to see which parameter actually influence the mode for the prediction. And I mean, we also expected, but not surprisingly, that when we compare the average F1 score, the higher F1 score, it means that the model work better in prediction. And we see that, for example, 1K here is the support vector machine combined with like 1D is the hydrodynamic model, give the highest F1 score. And all the parameter we have, we see that the minimum air temperature is the one that could affect the prediction of the mixing dynamic the most from the parameter. So you see that it is something that we expected from physics. But also one message that comes from here is that hybridly between AI and physics, it is a way to go forward. So by doing that, so you could actually solve two problems, like kill two birds with one stone, that you could reduce the number of equations in the physical base, and you also don't need many data to train as well. So it means that somehow it helps between both. In term of computational, whether it's expensive or not expensive, it's still a very expensive model to run. However, that for the term of giving the prediction, especially with environmental data, it's very scarce. You don't have a lot of data. Then combined with AI, with physics, it's the way to have it. And we also try to test it out with many other data. We call the project in knowledge guide machine learning, and we run that with water temperature for 300 river in Australia, and water stratification, DO, and also chlorophyll alpha. So far the project is still in development. However, I say that it the one that will help you to not just giving out the physics, the biology, but also to scale it up. You want to scale it so in many lakes. It's one of our ambition in aqua. It we to do for more than 200 lakes in Australia. So, and I also want to emphasize on this one that I also steal from Kate. So the model will tell you what can happen under different scenario and white chain and Mayaka, but it cannot tell you that whether the important processes are missing from the model. The data, it tells you what happened at specific location at the time, but it cannot tell you what happened that anything that not measured. So this is the message that powerful, that we need to actually have a validation combined between data or data-driven model and physics or physical-based model to actually building trust and deliver good results. I want to end my presentation with a framework that I'm still working on and seeking for collaborator. So in this framework, you can see that I try to improve the model. First thing is try to build a physical informed neural network for predict mixing and non-mixing to fit that into the growth model. And I also try to use deep learning for hyperparameter tuning. So this one will have for for the auto calibration of the both model, but it also have for the estimation from the sensor. So you know that some of the conversion from the sensor, it need to have some certain calibrated algorithm, and with JIT1 you could actually run a high level many optimization of hyperparameter to get the best estimation. So in JIT-K it from the higher spectra to cell count. And with this case, we also hopefully that we could deliver that on an Apple Watch web service. So whether it's stratification, mixing product, or other forecasting product, and many more. Yep. So this is the one that one I am seeking for collaboration. So hopefully that anyone here or online, if you have any idea or anything that you want to collaborate, here's my contact. So thank you for listening, and hopefully that the talk is enough to raise some of the interest from the audience on modeling and that data driven and physical by model. Thank you.
Thank you very much. Very, very interesting and very insight.
Bây giờ mình chuyển qua cái phần câu hỏi nhé, đặt câu hỏi nhé.
And
Xin
the
lỗi
modeling.
Duy với lại Professor
Now
Dũng
I
không
think we
nghe
have
chị nói.
about 15 minutes for question and answer. For the audience attending online, please type your question into the chat. For the audience in person, you can raise question.
So there are a couple of questions from the online audience. So I will read the questions one by one, and probably you two can respond. So the first one is addressing Mr. Dũng. Thank you, Dũng, for the broadcast sensing network. How do you plan to supply power to just a sensor? Battery will have a limited time life. Wiring is not practical. Do you think remote charge is possible? Noting that sensors may be 50 centimeters underground and can move over time.
Yeah. Thank you very much for the very, very important question. This is from Professor Long Nghiêm, right? Yeah, thank you very much. Yes, I think the energy, the power supply for the sensor is very important. And currently, the main technology is using the solar panel, and we charge the battery. So using the solar panel and battery. So that is the main point. And to reduce the power consumption, we need to have some strategy. For example, using the sensor that consume less power consumption, and also using the wireless communication technology that also we have to select the type that I mentioned. For example, the LoRaWAN or NB-IoT use very little power that is suitable for IoT application. Thank you very much.
Yeah, the second question is which supplier should we choose to invest IoT? Mr. Nguyễn Thanh Nhi has the system for agriculture.
Supplier.
Yes, supplier.
Okay. Yeah, I think maybe your question about what kind of IoT wireless communication, I guess. So I mentioned depending on the specific application, if possible, we use LoRaWAN that is developed by ourselves. We don't need to have the license, and that technology is suitable for the area, remote area, especially when the 4G, 5G are not available. And yeah, so for LoRaWAN, we can develop by ourselves, and for NB-IoT, that is when we need faster transmission. So in that case, we need to use 4G, 5G. Yes, so hopefully that answers your question.
Yeah, the first question is, if we get wireless disconnection, would the sensor have memory to store data and upload when the internet is back?
Yes, I think nowadays we can have the very good question as well. Always we think about how to store data at the node. Maybe we have a data logger, and then it can store some amount of data, and when the wireless connection is back, we can transmit. That is possible. Yeah.
So the rest of the questions may relate to this presentation. Should we calibrate anytime, or we have a library of equation when it comes to measure salinity? How often to calibrate?
No, it all depends on the type model you want to use. So for example, that a forecasting model, and then you depend on the driven input that you want to put into the model. Then if that driven input need to calibrate when it's moving, then you need to run the calibration. However, when it comes to other type model like the one that we use in for cyanobacteria, for example, and it's in a lake some of the lake is very stable system. However, that like say that if that cyanobacteria it many changing of the species seasonally or yearly, then every time like that you need to calibrate. But some of the system is very stable. You don't need to run. One of the things that I noticed is, for example, when I do like modeling, and when it comes to temperature, I just only give one-time calibration, and it could run all year round, give a very good result. So for that case, that you don't need to calibrate.
So thank you very much for interesting presentation from Professor Zui. And Zui, I would like to ask Zui how other colors will affect the chlorophyll detection, as cyanobacteria could have red color. Also, what is shelf life of the sensor when we put it to the water?
Okay, so the first question is about the color. So cyanobacteria, like the one that I give there, is actually on the greenish side. So it gives something it called the 3-band algorithm on the near red band and red band. However, other color could be detected as well. For example, turbidity at the gray color, then you use the index, it called NDTI. It comes from green band and red band combined together. And also thermal sensor for temperature, and it comes to cyanobacteria with the red color, we would have an algorithm for that as well. And the second question is the life of the sensor. I get that you want to add the high-res spectra. So that one is kind of semi-permanent. We actually have a 20-watt solar power connected to it, and it is above water. That is also important because a lot of sensor nowadays, when it's installed in water, it run into the problem of maintenance and the lifetime, but it is above water. So the one that we install in Vietnam, because many audience is Vietnamese, we install in Vietnam with the Vietnam weather environment and all that, etc. The only time that we need maintenance is actually back in September last year. That year when we have a really huge typhoon coming in. Other than that, we don't need to care. Anything else, and I think the most challenging when we install such a sensor in Vietnam is about security. You need to hire a person to watch it all the time. We don't have that in Australia here, but in Australia we also have other problems. You have birds, you have many wildlife and all that thing. So each country have that, but come back to the time, it's semi-permanent. It could run for a very long time.
So could you explain the possible uncertainty when using a 1D model for lakes?
Well, many uncertainty because first of all, it's 1D, so it's vertical. You cannot describe the horizontal process. So in lake, you have many horizontal process. You have the input of the inflow. You have the wind coming in and the wind spread and a lot the wind creates a long move. It means that it goes the circulation that come in the horizontal way and all that thing. So 1D, of course, it cannot describe that. However, the powerful of 1D is that it very light to run. So the model that we run for lake here, it run with 10 years of weather data, but it run under a minute. And for that kind of thing, you could actually install that any location to actually give an operational term of operational for the end user if they want to run that one. 3D, of course, everyone want to have a 3D model. However, 3D also come with like computational cost, running time, and also more complicated to solve as well. So if I only want to know about my temperature profile, then for me, for the purpose of what I'm doing here, then the 1D is also good enough.
Do you have any recommendation for setting up water quality model for tropical cases?
Yes, so most of the river or the lake in Australia is temperate lake. It means that you have a distinct season of summer very hot and then winter very cold. You don't have that in tropical in Vietnam. So in tropical lake in Vietnam, it's very dynamic and it's very unpredictable. It means that sometimes the lake is warm, but suddenly it get the mixing up, and then it also have some stratification in any time of the year. So that unpredictable is also risky. However, that is also one of the things that need to be aware of when you try to do the water quality model in tropical lake. Also a risky business as well. So in case of aquaculture farm, for example, then the fish or the sea animal, it depend a lot on the dynamic of that, and with that unpredictability, it run into a very tricky business. So that is one of the recommendations. You need to actually be careful of how you monitoring the dynamic for tropical compared to temperate environment in Australia.
So the other two questions is addressing Professor Dung.
Oh.
Would like to know more about LoRaWAN server connection that you developed. Could you please share more?
Server connection.
Yeah,
Yes. Oh,
The LoRaWAN.
LoRaWAN. Yes, we use the things network to get the data from the LoRa node. That is available in Australia and is free of charge. Yeah.
Another question: have you built up the pH sensor for water IoT? Thank you.
Yeah, thanks for your question. The pH sensor. We haven't developed a pH sensor yet. However, we know how to make the sensor. Yeah, we have the technology to make a sensor, but we haven't made that one by ourselves so far.
Thank you. I think that's all the questions from the online audience. Do you have any questions from the group here?
Is there any question from the?
Or not question, maybe a comment or anything?
Yeah, comment from
I have a
the.
couple, yeah.
Yeah, couple.
Yeah.
Well, I'll start with Zui. With the software, I was quite interested because I have a PhD student now that she's developing a 3D model for the broad water here to predict a specific species of algae.
Yeah.
And she realized for the main component, the aerodynamic component of Mike, just DHL
Yeah.
model. So with the 1D that I guess you develop your own 1D, is there any commercial software that you compare yours with to check accuracy and benefits? Or, I mean, how do we know, I guess, if I need to decide between using, your model or an existing sort of commercial model that does sort of the similar thing, how do you quantify the benefits of your model? Did you test the accuracy? Is it better in terms of accuracy to 1D existing software?
So to be honest, that we run the model and then testing against the sampling or measure data. We also test that out with other like GOM. It also another 1D model. And in terms of if jump is 1D, you like say that back to the same kind of turbulent model, the equation that I saw earlier. Then it when it comes to that, how many components that you have in like GOM, you could coupling between hydrodynamic, between chemical and biological at the same time. For my case, it needs to run hydrodynamic separately, get an input and into the grow model. But in terms of accuracy, I don't think there is much difference between the two. However, I'm not sure about when it comes to 3D. Other modeler, I think that for sure that if you have a 3D model, it would be better. But it's better in the case of you run like a small in laboratory setting. If you go out in a very large lake, it means that your grid size, it also need to be larger. And maybe that also kind of a minor point for accuracy. So not sure about comparing.
Yeah, no, definitely. That's one of the problems, that it's very slow to run. The 3D one, even more than the 1D, if you do it with the fine grid size.
So actually, when we work with Melbourne water treatment plant, water treatment, it's not just one single lake. It have a pond and can connect to the next pond, And we actually develop using 1D. So we use 1D for one pond, get the output, and then you 1D and just add an input for the next pond like that. And then we run that. It's very fast. But by a kind of a chain system like that, we feel like, okay, it maybe because we compare that with satellite data for that for temperature and then chlorophyll. And we can see that for a chain like that, it could also work a very good one. And if you are 3D for that type of thing, it take forever. Yeah.
That sort of links to my second and last question for you. When you check the accuracy for the 7 days forecast, because you rely on weather forecast as well.
Yep.
Do you run just one simulation, or do you have like an ensemble where you account for, like things like the wind forecast, like sort of change all the time?
Yeah. So the current system in AquaWatch, we run it daily, but we could increase the running frequency. And I have a study try to see how the changing of the weather model would actually affect the forecast. Most of the weather model nowadays only give around 7 days of temperature or weather forecast, but Google recently built their very good model using machine learning, and they claim that they could give around 15 days of weather forecast. So I want to see that, try to compare between all of that model, how that will affect the changing of my forecasting results. Yeah, but I say we run daily, and every time we have the data fit in. It is commercial data, but it also better if we have data from real time from that sensoring method weather station.
Yeah, that would be great. I had the same problem during my PhD because I have to predict 7 days ahead water quality in a lake. And yeah, the weather data were always a bit the problem sometimes because they change a lot.
And it also depends on the parameter you want to run. So some parameter get very direct from physics, like temperature. Then it have a good prediction. But other parameter like DO, dissolved oxygen, then it needs some certain type proxy in the model. Then that one will become a mess into. So we have a deep learning project actually. Try to compare between all the model, and we see that for DO after 48 hours, so the 2 day or 72 hours, the one that we run with the data from deep learning, it's actually get a better compared to the hydrodynamic here. So maybe the physics, when it comes to other parameter, it's not as good as some direct like temperature.
Thank you. And just very quickly to Professor Zoom, About the LoRa again, with the data transmission volume, what is the sort of the amount of data which makes it feasible or not feasible? So for instance, if I have one of those vertical profiling systems that you showed, that maybe they collect 5 water quality parameters every hour, is that too much?
No,
or
no,
is
that is very easy.
Okay.
So I think it's about up to 50 kilobit per second. Per second. So I think it's possible. It's difficult if you want to send image, then it's maybe not possible. But for sensor data, it's every minute. It's very straightforward. Right.
I think the last questions. For Duy, do you have any project in the central coast of Vietnam where there's complex weather condition?
Not just for now. And that is also one of the problem actually when I coming to Vietnam, it many heavy funding go to the Mekong Delta. And I think because Mekong is very popular, but that is also one thing we know that so many things happen in the central coast, but how to direct funding there, that is a huge question. Unless someone online actually working for the government or something, if you listening, then yeah, we're looking for that.
New collaboration.
Yeah, and then there's also questions for contact from Professor Dũng and Duy. I have already asked Chị Huyền to put up your contact detail there so that people who are interested maybe contacting you and asking for further questions.
Yeah, that's good. Yeah, thank you.
Any question from the audience?
Yeah, I think it's time.
Okay.
So, if we can
have time.
Yeah.
All right. First of all, thanks very much. And it's about 40 years, and I haven't been to the mechanical and physics, formula. So probably, it's depressed my mind. I have no idea what it's about. The thing I want to touch on here is similar to your question before, because it seemed to me that you built by both Professor Dũng and Dr. Duy, you do a good work for the modeling. The other thing I want to see, or I may not understand completely, is the implication of the model or the implication of your work here. I'm talking about, for example, we certainly will have some potential and some reasonable chance to get some funding from the community or from the government in Vietnam. In terms of right now, say for example, the farmer in Vietnam, if you build the prediction or the modeling or whatever to show that your water is not very good, so what is the solution to make it not harm like that? Or can we modify them, or can we change them to make it better? And that will be the impact from the modeling. So that's the first idea.
Yep.
The second idea, follow up, with the like a validation of your model, or promoting of your model, even just one day, even with a sort of we're using, because there are two things very important from the health and the implication for using the people is the feasibility and the acceptance of the people on the ground. So if you have all those beautiful well monitor, evaluate, you can tell the people that here's the thing that we really want to apply. So if I have a farm with some information there, if I want to check my quality, and it will be a lot of implication. We have been through the southern part of Mekong Delta River for the last few years, at least 5 to 10 years, and everybody talking about the quality of the water and how we can make it better. and people using traditional way, people using, you know, some not sort of, you know, scientific way, and they're dealing with that. And now we have, you know, it's look like, you know, we have good monitoring system or prediction or identify, you know, with even very detailed, you know, of the chemical, the bacteria, all of that, you know, it's very, very useful, you know, for the people, you know, on the ground. I just want to see, you know, how it can be collaborated, or maybe you already done that, you know, in a different way. I know that, you know, CSIRO have a very major, you know, input into all of the dam and the water, you know, station there. But, you know, in terms of on the ground, you know, practical, and I think we definitely, you know, we have very high chance, you know, to get, you know, some funding, you know, to get on the ground. That my, you know, comments, you know, in there, and definitely, you know, we should contact later.
Yeah, thank you, Dr. Han. I think that is very, very good comment. And today our webinar more about we detect the quality of the water, and then we give the prediction or warning to the user. And I think the next we need some expert in water, like the Edo, or we have some online people who can recommend how to treat the water for the drinking water or for the aquatic application, like horticulture, the fish, and so some expert in that area will recommend how we treat the water. It is not ideal for those applications. And that is a good application for future grant. We need a team, big team, one with working with the sensor IoT technology, one work with the modeling, and one work with the as user and recommend how to treat the water. So we have a complete team to from the detection, treatment, and recommendation. So that would be a nice application, very strong application.
Just adding to that very quickly, the project that we were together in Thailand and slightly getting into Vietnam, that which is funded by DFAT and the Australian Water Partnership, is exactly what we're doing. Yeah, I mean, there is the modeling and monitoring part that we are mainly involved with, but there is all the community engagement component as well. So we run a lot of workshops on the ground to show them, sort of train them, this is what you need to do based on the fact that this is the water quality that you have. So totally agree.
And it also coming back to the origin as well. So from the end user, they could report, okay, we are the one who provide information or early warning, but what type of early warning you want us to, then you need to communicate with me as a modeler. And then I know that, okay, so kind of parameter I need to give out. I need to talk with Professor Dung here, who designed the sensor to give out that. So it all at the chain. I think that many people say that to have a successful project, you need 3 T, you need time, and a lot of time, and you need trust, and you need tea. You need to sit down on the table, drinking tea and talk to each other. And at the Australian way, we also need the 40, that we need team time as well. Other gift to build relationship, because you need relationship. So you need that 40 to actually have a model. Back to that one small comment on your implication and resolution. For example, in a shrimp farm, if the farmer knows the information, like tomorrow they know that the water quality gone bad, they could have so many preparation. They could change the water, or they could decide to put more feeding in or not, or maybe move the shrimp somewhere else. So like Professor Dung say, we give the information, we give the early warning, but we need other experts and also the community to work out the solution. And of course, a lot like you say about the One Health concept, that is also one of the big part of AquaWatch. There we got working with water quality, and that's why we also involved in that part as well.
Very good. Is there any other question, Dr. Van? expert in sensor. Actually, I forgot to mention.
Okay.
Yeah.
Thank you. Thank you. We actually have a team working very deep in CFD, so I try to set my head around your 1D model. I think it is true that we use 1D because in the lake, so we say we suppose the horizontal fluid flow is not very serious.
Yeah.
So can we apply this model into sites like river or basically, I guess my question is how do you interpolate your fluid dynamics parameter into your model? And also I look at the equation. I guess it's very hard to define the growth vector of that vector because it looks a little bit simplified. But I guess it's not appear as simple as it is. So any like experiment validations so how basically that's the I really want to know the reason why it's the 1D vector being that good.
Yeah.
That's like magic to me. And also the growth vector and the dash vector of the vector. So I guess lots of things happen behind the screens, but
yeah. So the first thing about the model is actually the input, many parameter input, and you need to calibrate them. And to calibrate them, we do it manually before. And to do manually, you need to have some expertise. For example, you go to Ranong, you know it is shallow lake. You know from your knowledge, you know the dynamic of it. Then you could give some of the prediction on some of the range of the parameter you want to calibrate, and then you go from there. But that one, it means that it takes time and it needs experience and expertise. The next thing we try to use hyper tuning. It means we let the machine to do that for us. So many algorithms out there for hyper tuning. It could run up to, like in our model, every time I calibrate 18 parameters, and it could run that, and it could give me a really good calibration for that. And we also have some estimation, like for example, we give them in the model. For example, if I want to move on into the Melbourne water, when the water go from one pond to the next pond, it means you have the water inflow and the water outflow. Then I also try to put that parameter at an inflow and outflow into my 1D model. So it means that you add up a lot of things. It's 1D, but then you add up so many things in there. And for the growth dynamic, like I say that it on for my model, I only make it depend on light intensity, on the temperature and mixing dynamic, and then I estimate for example, if I want to model microcystis, and I understand that microcystis is kind of changing density when it's buoyant and that thing, then I would know that how could I set up my parameter in the growth equation. So you are correct. In the background, behind there is so many things. That is one part that the machine still cannot replace me. I'm not unemployed. That we got still they need the expert on that one. However, like I say, when we go into deep learning and go to multi-optimization parameter, so maybe in the future, the one that not from the CFD field at all could actually run and use the model. That is what we want.
Thank you.
Yeah. Yeah,
Okay, thank you.
And I say that the biological is very complicated, and yeah, everything comes from biology. So
Okay, so I think we are running out of time. I think I thank you very much, everyone, for attending this webinar, and I think we finished our today. Thank you, everyone.